Okay, good afternoon everyone. I welcome you all to the second tutorial of this course, Introductory Organic Chemistry 2, which is conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Niraja Dashaputre from ISER Pune. I'm your PMRF teaching assistant for the course Introductory Organic Chemistry 2. I'm Deepika and I'm pursuing my PhD in chemistry at IIT Bombay. So today is the second tutorial for this course. Last week in the first tutorial we solved a few questions on electrophilic aromatic substitution reaction and also essentials of NMR spectroscopy. So today we will continue the same topic, electrophilic aromatic substitution of phenols, and also effect of activating and deactivating groups in benzene ring when it comes to substitution reaction. Also, we will solve a few questions on the topic essentials of IR spectroscopy in organic chemistry. I hope my slides are visible and I am audible to you all.
Yes, sir.
Okay. So, before moving ahead for today's tutorial, actually in last week's tutorial, one of you asked about the assignment of first week. I think it was Lalita, if I remember correctly. So, actually, I tried to find the assignment for week one, but it seems we, the PMRF teaching assistants, do not have access to the weekly assignments, but we can only get the previous year assignments. So, if you want the solution to the previous year assignments, then I would suggest you to go through the week one tutorial of another PMRF teaching assistant of the same course, who is Anisha Suresh. She has uploaded her video of week one in her YouTube channel. Currently, I do not remember her channel's name, but I will try to find the channel's name and mention in the maybe in the next week's tutorial. But if you want the video, you can get the link or get her channel's name, Anisha Suresh. She has solved the previous year assignment questions in last week's tutorial in her channel. And about this year's assignments, we do not have access to this year's assignments. Okay, so you all will have to solve them by yourself. So in our tutorial, we will just try to solve a few sample questions related to the topics taught in the course. Okay, so let us move ahead. And also, the recordings of these tutorials for my time slot will be available in the YouTube channel Tutorials by Deepika. If you do not find in the next week's tutorial, I will show you going to the YouTube, which channel I'm talking about. It is Tutorials by Deepika. You will get the recordings of the video uh, tutorials of every day. Okay. So with that, let us move to today's tutorial. So the first question of today's tutorial is, what will be the product formed when phenol reacts with bromine in carbon tetrachloride medium? So you are given four options: 3-bromophenol, 4-bromophenol, 3,5-dibromophenol and 2,4,6-tribromophene. So what happens in carbon tetrachloride, which is a non-polar solvent? In this non-polar solvent, bromine liberates a very weak electrophile, which is positively charged bromine. Okay, so the weak electrophile Br plus is generated in the medium, which gets attacked by phenol. So now phenol contains one OH group in benzene ring and OH group. If we talk about activating and deactivating and orthopara directing versus meta directing effects, phenol has orthopara-directing activity. Okay, we will go through the activating and deactivating and directing chart in the subsequent questions. But as we all know, if a substituent on benzene ring has lone pair of electrons on it, then it is always orthopara-directing. So OH of phenol is orthopara-directing group. Then we can expect that when it is reacted with the weak electrophile generated Br positive, we can expect either 2-bromophenol or 4-bromophenol or 2,4,6-tribromophene. Okay, bromine will be introduced only on the ortho and para positions. So out of these, we can directly eliminate the options option A and option C, because these are showing the formation of meta bromination, which is not possible for phenol. So now we are left with option B and option D, 4-bromophenol and 2,4,6-tribromophenols. So what happens? Because of the weak electrophilicity of Br positive formed in the nonpolar solvent CCl4, only monobromination is possible in case of this reaction given here. Okay. So due to this reason, only one bromine will be introduced to the phenol ring. Tribromination will not possible in this non-polar solvent reaction condition. And here, as you can see how the Br positive electrophile is getting generated, it is by weak dipole-dipole interaction between it is due to the weak dipole-dipole interaction between the bromine atoms in Br2. Okay, so always remember, in this particular reaction only monobromination is possible. So option B is the correct answer out of B and D. So after this question, let us move ahead to the next question. What is the electrophile in the electrophilic substitution reaction of benzene using oleum and concentrated H2SO4? In the last week's tutorial also we learned about electrophilic substitution reactions various and we thoroughly discussed the mechanism of nitration also. Okay, so this particular reaction condition given is talking about oleum and concentrated H2SO4. Now what is oleum? Oleum is H2S2O7. It is a highly acidic reaction condition, even more acidic than concentrated H2SO4. Oleum is a mixture of concentrated H2SO4 which contains SO3 in it. Okay, so this particular reaction condition gives sulfonation of benzene. How is it possible? Let us discuss the mechanism of this reaction. Okay, what happens? This is H2SO4 in the reaction medium, and as we know, oleum contains SO3, major portion of SO3 in it. So these two reacts, and this SO double bond takes up a proton from H2SO4, generating the desired electrophile, which is sulfonium ion here. Okay, so this SO3 gets generated and liberates, so this liberates this anion here in the reaction medium, but this active electrophile undergoes electrophilic addition with benzene. So like we discussed the mechanism last week, this will also undergo in a similar fashion. The benzene ring will attack on the electrophile, on the positive charge, leading to the formation of this sigma complex. Okay, and this is the rate determining step, always remember. And then in the subsequent step, the sigma complex will undergo deprotonation by the anion present in the environment, and this anion will take up a proton, leading to the formation of the sulfonated product. So thus we can expect the sulfonation of benzene where SO3 is acting as the electrophile. You are given these four options in the question and only option A will be the correct answer. And this benzene sulfonic acid will be the product generated in the sulfonation reaction. This was a very easy question after the discussion that happened last week. Okay, so in the next question we have, which of the following aromatic compounds undergo Friedel-Crafts alkylation with methyl chloride and aluminium chloride? You are being asked that methyl chloride and AlCl3 is given in the reaction condition, and out of all these possible substrates given in the option, which one will undergo Friedel-Crafts alkylation? So before knowing the answer, you must remember the reaction conditions and reaction mechanism for Friedel-Crafts alkylation. Okay, what happens in Friedel-Crafts alkylation? It is an electrophilic substitution reaction. So, for electrophilic substitution reaction, the attacking aromatic ring must be electron rich, because in the course of the reaction we are going to attack on the positively charged electrophile. We are in a way giving up electrons from a electron rich system to an electron deficient substance, which is the generated electrophile in the reaction medium. So if you want to give up electron, you need an electron rich system, because you cannot donate electron from an electron poor moiety to an electrophile. So for that we just need to now screen the substrates which are electron rich enough that it will give up its electrons to the electrophile. Okay, and definitely electrophile here in this reaction condition will be Me plus. Okay, so which substrate of out of these will give up its electron to Me plus? Is it benzoic acid? Is it nitrobenzene? Is it toluene, or is it aniline? So let us talk about the substrates one by one. In benzoic acid, COOH has an electron withdrawing effect on the benzene ring. Okay, so due to its electron withdrawing effect, the benzene ring is becoming electron deficient. So it cannot give up its electron to the electrophile. That is why we can cross the option A. Similarly, option B, nitrobenzene. Nitro group is strongly electron withdrawing group. Okay, so as nitro group is also making the benzene ring electron poor, electron deficient, it also cannot undergo electrophilic substitution reaction. Now we are left with toluene and aniline, and toluene contains a methyl group on the benzene ring, and aniline contains an amine group on the benzene ring. Both are electron donating in a way. Okay, toluene has an alkyl group which is electron donating, and aniline has an amine NH2 group which has lone pair of electron, and it can easily donate its electron pairs. But out of these two, only one can undergo Friedel-Crafts alkylation. Why? The reason is that aniline has a lone pair of electron. Okay, and in the reaction condition Friedel-Crafts alkylation, we are using a Lewis acid, which is aluminium chloride, AlCl3. So what happens when we add AlCl3 to aniline? The lone pair of amine helps it in making a salt with the Lewis acid AlCl3. So AlCl3 directly forms a salt with aniline, due to which it is not available for the generation of the electrophile. In the mechanism, what we saw, aluminium trichloride reacted with the alkyl iodide, generating the alkyl electrophile. But as in case of aniline, this reaction is more favorable. Okay, the lone pair of electron gets donated to the Lewis acid and forms a salt, and makes the salt unable to undergo electrophilic substitution reaction. So this is why, even though in aniline NH2 group is electron donating and it should make the benzene ring electron rich, but this competing reaction which forms the salt prevents aniline from undergoing Friedel-Crafts alkylation. Okay, so out of these all four options, only option C will undergo Friedel-Crafts alkylation. Here, the short explanation is given, but in case of aniline, it will not be the reason that it is electron withdrawing. In case of aniline, it is because it forms the salt with the Lewis acid in the reaction material. So with this, we have gotten the answer C. Next question is, which of the following is the most activating in electrophilic aromatic substitution? You are given four options: nitro, amide NHCO3, CN cyano, and NH2 amine. So you are being asked, if these four substituents are present in the benzene ring, which group will be the most activating in electrophilic aromatic substitution? Presence of which group will make the benzene ring the most electron rich so that it can undergo electrophilic aromatic substitution? Very easy question, like we saw in the previous questions, that to undergo electrophilic aromatic substitution, the benzene ring, the aromatic ring, must be electron rich. So you just need to screen the substituent which has electrons to be donated to the aromatic ring. Okay. So, okay. So out of all these four, like we have already discussed for the nitro is a very strongly electron withdrawing group. So it is deactivating group in case of electrophilic aromatic substitution. Okay. And in case of amide also, amide as well pulls electrons from the aromatic ring due to the presence of this CO carbonyl. Okay. Amide is also making the aromatic ring electron deficient. In case of CN is capable of forming synergic pi bonds in presence of neighboring electrons. Okay, it accepts electrons from the benzene ring, thereby making the ring as a whole electron deficient. Okay, as it pulls electrons from the benzene ring forming pi bonds, it is also deactivating the aromatic ring to undergo electrophilic aromatic substitution. And for amine, we know that it has a lone pair, unshared lone pair of electron on nitrogen atom, which can easily be donated to the aromatic ring. So this lone pair of electron is making the aromatic ring electron rich. So aniline can easily undergo electrophilic aromatic substitution. Of course, it cannot undergo Friedel-Crafts alkylation and acylation due to the competing reaction. But when it comes to other kinds of electrophilic aromatic substitution, aniline will easily undergo the reaction, making the aromatic ring electron rich. Okay, so out of the four options given here, option D will be the correct answer. Okay. So moving to the next question, which is the correct order of reactivity toward electrophilic aromatic substitution? Similar question, okay, just different substituents. By now you must know what kind of groups are activating and what kind of groups are deactivating towards electrophilic aromatic substitution. So easily you can rate these four substituents in terms of reactivity. Okay. So this will be the correct order. See, in case of methyl and methoxy, when methoxy is present in an aromatic ring, the lone pair of electrons on the oxygen atom can easily be donated to the aromatic ring, which gets delocalized an entire ring, making the ring as a whole very electron rich. And this methoxy substituted benzene will then easily undergo electrophilic aromatic substitution. Thus, when it comes to methyl versus methoxy, methoxy makes the ring richer. Okay, and uh, when we compare CH2F and COOH, CH2F is still a alkyl. Okay, still an alkyl. Just one hydrogen is being replaced by fluorine, which is a highly electronegative atom. So it is still an alkyl. And when it comes to alkyl versus acid, alkyl is more electron donating. This is why it is placed on the third position of the series. And at last, COOH, which has electron withdrawing effect on the aromatic ring, so it will be least reactive towards electrophilic aromatic substitution, and thus you get this kind of series. Okay, this will be the correct order of reactivity towards electrophilic substitution. Then another question from the same topic, deactivating and directing effects, which is expected to be the major product for the following reaction. You are given the substrate and you are subjecting it to bromination conditions in presence of bromine and FeBr3. So just like AlCl3, we are taking here the catalyst FeBr3 and you are asked which product out of 4 possibilities will be formed. Let us screen the products one by one. Okay. And first let us look at the substituents already present on the benzene ring. One is methyl and one is acetyl, CH3CO. Okay, and out of these two, you must know CH3CO, due to the presence of this carbonyl bond, carbonyl uh, functionality in the molecule, this CH3CO has electron withdrawing effect on the benzene ring. Whereas this methyl group, being an alkyl substituent, has electron donating effect to the benzene ring. Okay, and both of these two have different directing effect. Alkyl is orthopara-directing, whereas this keto group is meta-directing. So how are we going to manage now? Let us look at the options one by one. Okay, in option A, we are seeing that the bromine is taking a position which is present ortho to both the substituents present. Okay, in terms of methyl, definitely bromine is obeying its activity. Okay, because it is ortho and para directing group. So in terms of methyl, it is obeying its effect, but in terms of acyl, it should be forbidden. Okay, introduction of bromine should be forbidden in terms of acyl. So still, let us keep option A in hand since it is obeying the methyl activity. Then let's come to option B. We see that it is in the position meta with respect to both the substituents methyl and acyl. Okay, and in option C, you are seeing that the ring is not undergoing electrophilic aromatic substitution, but it is giving bromination in this methyl. Okay, in presence of the reaction conditions present, bromine and FeBr3, which is electrophilic substitution condition, these kind of substitution reactions are not observed. Okay, for this we may need to involve highly basic reagents. Okay, so option C can directly be cancelled for this reaction condition. And in option B, let us look. We see what is there. Bromine is present ortho to the methyl but para to the acyl. So like option A, option D is also obeying the effect of methyl group but disobeying the effect of acyl group. Now let us talk about orthopara directing versus meta directing groups. When you have two substituents in a ring, one of which is orthopara directing and the other is meta directing, and they are competing with each other, the orthopara directing group always suppresses the effect of the meta directing group. Okay, by experimental research it is always found that always the orthopara directing group directs the incoming electrophile, neglecting the effect of the meta directing group. So when methyl and acyl groups are present in the benzene ring, the orthopara directing group will dominate here. So keeping this fact in mind, option B can be cancelled, because we are seeing that in this particular option the meta directing group is dominating, which is not seen in the experimental chemistry. So option B and C are now out of the frame, and we are left with option A and D, and you need to find the major product formed in the reaction. See, both option A and D are possible, okay, both can be formed, but one factor which will be deciding the fact that which one of these will be major and which one will be minor is none other than the steric factor. Okay, so as you know, in organic chemistry steric factor plays a huge role in all kinds of reactions. So in this particular reaction also, steric factor will play its role in giving the major product. So out of A and D will be the most sterically favored product. Okay, and A will be the minor product formed in the reaction. So when you are given this reaction, in presence of this reaction condition, out of all these four possible options, option B will be the correct answer. Okay, and this is the table which is showing the activating and deactivating groups in approximate order. So you may go through this table, or you will find this table in numerous organic chemistry books as well. So this is the order which the substituents present in the aromatic rings follow. Okay, so this will be very helpful in deciding what kind of major product you will get in electrophilic substitution reactions. So like we saw here, option D will be the correct answer. Okay, I hope that was clear, and let us move to the next question now. Which of the following is compatible with a Fischers reaction? You are given an acyl substituted benzene, and then in another option you are given nitro and chlorine, and in option C you are given this option where the benzene ring is containing one methyl and one amino substituent, and in option D the question is saying that none of A, B and C are compatible for Friedel-Crafts reaction. Okay, since we have already discussed a lot of questions on this topic, so you may know already the answer. The answer will be option D. Okay, why option D? Because in case of option A and B, you all know that in A we have the deactivating group, since the acyl group is making the benzene ring electron poor, so it will not be compatible. And in case of option B also, both nitro and chlorine are deactivating. Okay, why nitro? Because nitro is a highly strongly electron withdrawing group, and Chlorine is also, due to its high electronegativity, it is electron withdrawing group, and these two both are making the benzene ring highly electron deficient, and that is why option B is also not compatible for Friedel-Crafts reaction. Option C, like we have discussed in case of aniline, although it contains electron lone pairs on it, which can be donated to the benzene ring and which get delocalized in entire ring, making it electron rich. But as it forms a salt with the Lewis acid given in the Friedel-Crafts reaction condition, it also makes itself incompatible for Friedel-Crafts reaction. Okay, so for this particular question, option D will be the correct answer, none of above. Okay, then we are moving to this very easy question. You are given this substrate in which you are treating it with acidic conditions, and you are asked which of these four products will be formed. Okay, so what happens in presence of acid? This kind of mechanism is followed for this particular reaction. Okay, this methoxy will undergo hydrolysis to give you enol, and this enol quickly tautomerizes to its more stable form, which is a ketone. Okay, so for this particular question, when you treat this methoxide in presence of acidic condition, you will get this ketone as the major product. Now we are moving to the next question. Arrange the following compounds in decreasing order of acidic strength. We have three phenol compounds here, one of which is completely unsubstituted, like pure phenol, one of which is containing nitro functional group, nitro substituent on the phenol ring, and the number 3 is containing a methyl on the phenol ring. Okay, so now you have to arrange them in decreasing order of acidic strength. You must know that phenol is highly acidic because after it donates its proton, phenolic proton, it forms phenoxide ion. Okay, the conjugate base after donating the proton will be phenoxide ion, and phenoxide ion can undergo conjugation with this phenyl ring, and that makes this phenoxide ion highly stable anion. Okay, and due to the formation of this stable conjugate base of phenol, phenol is highly acidic. Okay, now we have to look at the effect of nitro and methyl on the ring. Okay, so what happens in presence of nitro group, which is highly electron withdrawing, it is making the ring electron deficient. Okay, so when the anion will be generated on the oxygen atom, this anion will be pulled more towards the nitro, which will make the anion formed after donating the proton more stable. Okay, this anion will be more stable due to electron pull from this nitro. But in case of methyl substituted phenol, see, after the formation of the anion on oxygen atom, it is already electron rich. Okay, and it will try to donate its electron pair to the ring. But in case of the para substituted methyl, it is also from this direction giving up its electrons. So basically both these sides will try to donate their electrons to the benzene ring, which will create a sort of electron repulsion in the system. This is why the phenoxide ion formed after donating the proton will be a little destabilized in presence of electron donating groups on the benzene ring. Okay, so if we have to arrange these three, we must know that nitro is making the phenoxide ion more stable and methyl is making it less stable. So out of these three, nitro substituted phenol will be the most acidic one, followed by phenol, completely unsubstituted, which will be followed by option number 3, which is methyl substituted phenol. Hence, the correct answer will be option 2. Okay, here you have a general explanation on the electron pair acceptors and donors. So you can go through this list also when it comes to acidity and basicity, but we will not take much time on it because this topic was already covered in the topic Introductory Organic Chemistry 1. So for this particular question, the correct answer will be option 2. Let us move to the next question now. The following conversion is: you are given bromophenol, bromobenzene, and we are treating bromobenzene with sodium hydroxide, and the product liberated here will be phenol. Okay, this is a process which is synthesizing phenol from bromobenzene. So you have to identify what kind of reaction it is. Is it free radical substitution? Is it electrophilic substitution? Is it nucleophilic substitution? And or it is aromatic addition. Okay, definitely it is not free radical substitution because the reaction is not undergoing through a free radical intermediate. Let us look at the reaction mechanism closely and try to understand what kind of reaction pathway is it following. Okay, so there is a process which is called Dow's process, and Dow's process is used to prepare phenol by reacting halobenzene with sodium hydroxide. Okay, and this reaction particularly is carried out in very high temperature. This is the mechanism which this reaction follows. Okay, what happens? The halobenzene first undergoes a reaction with sodium hydroxide, which liberates this kind of anion in this reaction, and this anion is highly unstable and it breaks down into this reactive intermediate which is known as benzene. Okay, this reactive intermediate benzene contains a carbon-carbon triple bond on the ring. Okay, so in the course of the reaction, benzene gets attacked by hydroxide, an ion of sodium hydroxide, leading to the formation of this aryl anion. And then this carbon ion will undergo reaction with sodium hydroxide, liberating phenol as the final product. Okay, for this particular conversion, you can show the arrow pushing as this anion will take up a proton from phenol, leading to the formation of this phenoxide, and then this phenoxide will take up a proton from water or acid present in the workup process reaction medium, and finally you get phenol as the product furnished via this reaction intermediate benzene. Okay, so thus this Dow's process undergoes a reaction where this nucleophile hydroxide attacks the reactive intermediate. So what kind of process is this? Is it electrophilic substitution or nucleophilic substitution? We are dealing with nucleophile hydroxide here, okay? So the option 3 will be the correct answer. We are substituting the halogen atom by the nucleophile hydroxide. Okay, so option 3 will be the correct answer. And remember this process, Dow's process, which is widely used for synthesis of phenol. Then let us move to the next question. Which among the following is the strongest acid? You are given here 4 phenol substrates and you are asked which one of all these 4 will be the strongest acid. So to know how option 2 is the correct answer, we must compare them to each other one by one, okay? So in case of all these 4, option 3 can be first eliminated because if we compare the electron withdrawing effect of nitro and chloro groups, out of these two substituents, nitro is more electron withdrawing, okay? And as we know, if we want strong acidity of phenol, we must make its conjugate base phenoxide ion more electron deficient, okay? So for that, nitro will be the preferable substituent out of nitro and chloro. So out of all these 4 options, we will first eliminate the option 3. And we are left with option 1, 2 and 4. And these are the different resonance structures for phenol and ortho nitrophenol. But let us just try to understand the process easily, okay? See, nitro group is not nitro. The hydroxyl group present in phenol is ortho para directing, okay? And what happens when the nitro group in phenol is present on the ortho and para positions, they have more electron withdrawing effect by mesomeric effect and and their electronegativity effect. Okay, two electron withdrawing effects are working in case of orthonitrophenol and paranitrophenol. Okay, so when it comes to metanitrophenol, nitro group is withdrawing electron from the ring via only its electronegativity, which is in a way you can call inductive effect. Okay, so as we can see in case of 2 and 4, 2 effects are working in electron withdrawing effect. So when we compare these 3 to each other, ortho and para will have more electron withdrawing effect than meta. Okay, so presence of nitro on meta is also withdrawing electron but not as efficiently as ortho and para, because here mesomeric effect is also acting. So now we are left with option 2 and 4, orthonitro and paranitro. Okay, so what happens in case of orthonitrophenol? You can see that the NO bond of nitro group forms hydrogen bonding with the phenolic OH group. Okay, since in case of orthonitrophenol, the OH substituent is in close proximity with the nitro. It can form a very strong hydrogen bond. Okay, and due to this hydrogen bond, this hydrogen bonding makes orthonitrophenol a little less acidic than paranitrophenol. Okay, so due to hydrogen bonding, paranitrophenol will be more acidic. Thus, we compare the acidic strength of these four options given, and the most acidic out of these four will be option 2. Okay, so paranitrophenol will be the most acidic one. Then let us move to the next question of the topic, which is a very popular reaction of phenol. You are given a reaction condition here, and where we are treating phenol with chloroform and sodium hydroxide, and this kind of product formation is being shown. Okay, an aldehydic substituent is being introduced on the ortho position of the phenolic OH. So you are asked the electrophile involved in the reaction is it dichloromethyl cation or is it formyl cation? Is it dichlorocarbene or is it dichloromethyl anion? I'm not sure you have come across the term carbene and nitrene yet or not, but in this particular reaction, we will have an introduction of the term carbene. Okay. So what happens in this reaction condition? At the very beginning, chloroform will undergo reaction with hydroxide from sodium hydroxide to give this kind of anion first. Okay, actually this structure is not correct. It should be CCl3 minus. Okay, this proton should not be here. So in the subsequent step, this CCl3 will undergo dechlorination to give the reactive intermediate involved in the reaction, which is CCl2, and this particular electrophilic reactive intermediate is called carbene. Okay, it has, out of the 4 orbitals of carbon, 2 orbital will be empty for the carbene, and it is highly electron deficient moiety, and this electron deficient moiety is known as carbene, and it acts as the electrophile in this particular reaction. Okay, this reaction is known as Reamer-Timid reaction, and in this reaction, after the generation of this particular desired electrophile, the phenol ring attacks on the carbon atom. Okay, so the rest of the mechanism is similar to an electrophilic substitution reaction. The aromatic ring will attack on the carbene, and subsequently hydroxide ion will act to give you the desired aldehyde on the ortho position. Okay, mechanism of this reaction you can study for the topic Reamer-Timid reaction. Okay, but you must know that the electrophile generated in this reaction is CCl2 carbene. So out of the 4 options given, out of the 5 options given, option 3 will be the correct answer, dichlorocarbene. Okay, and this particular part for this question is very, very important in the topic reactive intermediates. Okay, with this we are moving to the next topic of today's tutorial, which is Essentials of IR Spectroscopy. We are trying to solve a few questions on the topic today. So, the first question for this topic today is, what is the correct increasing order of stretching frequencies for carbon-carbon triple bond, carbon-carbon double bond and carbon-carbon single bond? You have to arrange them in the increasing order of stretching frequencies. So when it comes to stretching frequencies in IR spectroscopy, it gives you the measure of energy required to stretch or eventually break a bond present in a molecule. Okay, so the amount of energy will depend on the frequency, and the frequency will in turn depend on the fact that how strong is the bond which we are talking about. And that strength is in general calculated by a physical chemistry formula, which was force constant, which was given in terms of force constant and mass. Okay, so this is the equation I'm talking about. Okay, if stretching frequency is given by nu is directly proportional to the force constant, and definitely if we talk about the mass, it will be inversely proportional to the root of mass. Okay, this you will study in physical chemistry, but when it comes to comparing the bond strengths or stretching frequencies in case of IR spectroscopy in organic chemistry, here we can see that in case of triple bond, the carbon-carbon bond is much stronger as compared to double and single bond. Okay, and this bond strength will dictate the stretching frequency of its IR. So, stronger the bond, more will be the stretching frequency. Always remember. So now you can easily compare the increasing order of stretching frequencies for the given bonds, and as you can see, option B will be the correct answer here. Now let us move to the next question. A compound C8H6 decolorizes bromine in CCl4 and gives a white precipitate with tolerance reagent. It has sharp band at 3300 centimeter inverse and weak bands at 3085 and 2110 centimeter inverse. What is the compound? So in the last week's tutorial, we tried to identify a few organic compounds structures by taking the help of NMR spectroscopy. And in this particular example, we will try to identify the compound in terms of IR spectroscopy. Okay, and we will go deep into the question while solving. So you are given these four options. Okay, phenyl acetylene, phenyl propylene, phenyl ethylene and octene. So now let us break down the stretching frequencies given in the question one by one. If you look at the IR stretching frequency values for different bonds, when it comes to carbon-carbon single bond, carbon-carbon double bond and carbon-carbon triple bond stretching frequencies, the carbon-carbon double bond stretching frequency comes at 1600 centimeter inverse or near it. Okay, it always ranges in that position of the band. And when it comes to carbon-carbon triple bond stretching frequency, it ranges near to 2200 centimeter inverse. It is mostly from 2100 to 2200 centimeter inverse in case of carbon-carbon triple bond. So if we look at the values given in the question, we can see a value which is near 2200 centimeter inverse, and we can see no value around 1600 region. Okay, so we already have gotten a hint that this compound that we are talking about can be an alkyne. Then what kind of frequencies are we given here? We have a 3085 value and 3300 value. So if we talk about CH stretching frequency for two types of CH bonds. One is which is attached to an alkene, like the CH which will be attached to this position, and the other will be CH attached to an alkyne. Okay, if we compare these two CH frequencies, this alkyne CH frequency comes around the region 3100. Okay, so this 3100 value, okay, sorry, not 3100, it will be near the value 3300. Okay, for alkynes, for alkynes you can expect a value which will be a very sharp band around the region 3300. So but in case of alkenes, the CH value will be a slight lesser, which will be around 3000 to 3100. Why is it so? You may ask why this alkyne CH stretching is giving a more value than this alkene CH. This is due to the fact that this particular CH is attached to a carbon-carbon triple bond, okay, which is sp hybridized carbon atom. And in case of these alkenes, these CH attached are attached to sp2 hybridized carbon atom, which are less electronegative than this sp hybridized carbon atom. So as this hydrogen atom is attached to a more electronegative carbon, the length of this CH bond decreases. Okay, and this short length CH bond is very strong CH bond, which leads to a very sharp band at a higher stretching frequency value, which is 3300 centimeter inverse. So if we look at all the four options given here, only one of these options is containing an alkyne CH bond, and that CH bond will lead to a value which will be at 3300 centimeter inverse. So thus you can expect that option A, phenylacetylene, will be the correct answer out of all. Okay, so with this we have arrived at the end of today's tutorial questions. Let us quickly go through the questions that we have discussed today. So we started with this question: what will be the product formed when phenol reacts with bromine in carbon tetrachloride medium? We talked how a very weak bromine electrophile is generated in this non-polar solvent, and only monobromination was possible for phenol. Okay, so in this question answer B was the correct answer. In the next question, we talked about the electrophile generated in the reaction condition where we are given oleum and concentrated H2SO4. We went through the mechanism of sulfonation and we saw how SO3 is being generated as the electrophile here. Okay, so the answer A was the correct one. Then in the next question, we talked about these four substrates and we talked how only toluene out of these underwent a Friedel-Crafts alkylation. Okay, and this question we stressed upon the fact that aniline formed a salt with the Lewis acid aluminium chloride in the reaction condition. And in the next question, we compared the activity of these four substituents towards electrophilic aromatic substitution, and we saw that option B was the correct answer, and this was the most activating substituent in case of electrophilic aromatic substitution. And then we compared the reactivity of these four substrates towards electrophilic aromatic substitution, and again we saw that the electron donating groups activate the aromatic rings towards electrophilic aromatic substitution. Then we talked about this bromination reaction and we saw that orthopara directing groups were dominating the meta directing group. Okay, and thus due to steric reasons, option D we got as the major product in this reaction. Then we talked which of these following substrates were compatible with Friedel-Crafts reaction, and we saw that none of option A, B and C were compatible. Okay, and the reasons we have already discussed. Then we went through this very easy reaction where we saw that how this methoxide underwent hydrolysis to give you enol, and the enol immediately tautomerized to its stable form, which is a ketone. Okay. Then in the next question, we compared the acidic strength of the compounds given 1, 2 and 3, and we saw how nitro was making the phenol ring more acidic by pulling the electron pairs from the phenoxide ion formed, and whereas in case of methyl, a sort of electronic repulsion was shown in the benzene ring. Okay, and so the option 2 was the correct answer for this question. Next, we came across the popular Rimmer-Timon reaction for phenols, and we saw, sorry, not this one. Okay, this was the reaction which was Dow's process. Okay, in this particular reaction, the bromobenzene was treated with sodium hydroxide, and phenol could be synthesized by this process, and the reaction was found to follow a nucleophilic substitution. And then in the next question, we again compared the acidic strengths of these four phenolic compounds, and we talked about various electron withdrawing activities of the nitro groups, and we saw why ortho nitrophenol was less acidic than para nitrophenol. Okay, and then finally we came across the Rimmer-Timon reaction where we saw that carbene was getting generated via the reaction of chloroform with sodium hydroxide, and this dichlorocarbene was the electrophile involved. Then we talked about the equation which was relating the stretching frequency to the force constant, and we saw that a stronger bond in organic molecule will have higher stretching frequency. And then lastly, we talked about the stretching frequencies of various CC and CH bonds. Okay, and we saw how hybridization of the carbon atom attached to a hydrogen was directing the values for the stretching frequency of CH bonds. Okay, and we saw why the alkyne CH stretching frequency is found to be so high. So with that, we have come to the end of this second tutorial questions. So thank you all for joining, and feel free to ask any queries that you may have for today's tutorial. Okay.